Okay, so let's look at section 4.9, related rates. Our objective is to solve related rate problems. These are problems that are going to be a little bit tougher maybe than what we've done, maybe not as any tougher than optimization problems, but still ones that stretch you. But they are incredibly applicable, so we really want to learn how to do this and to do it well. Okay, so let's start off with this. If you watched yesterday's video, it wasn't a required one, but if you watched it, I worked through this problem on yesterday's video. Pretty quickly here, it says given dx dt, and we're supposed to find dy dt. So that means I'm taking the derivative of this entire equation with respect to time, with respect to the variable t. So when I take the derivative of y, that gives me dy dt equals 1/2 x to the negative 1/2 dx dt, because there's not a t there. A lot of times with the x, we're not used to writing anything because we're used to doing dy dx. But on this one, there's no t there, so it's dx dt. Plug in your numbers, not a problem. I have dy dt equals 1/2. My x value is 4 to the negative 1/2. My dx dt is 3, so that's 1/2 times 1/2 again, because 4 to the negative 1/2, and then times 3. So pretty quickly we can see that dy dt is 3/4. Okay, given dy dt is 2, this time I'm supposed to find dx dt when x is 25. Well, this part right up here that we had earlier, I mean, let's just clone that little piece, because that piece is there again, okay? No difference at all. Derivative is the same, just different numbers that I plug in. So dy dt, I'm going to put in a 2 equals 1/2. My x value is 25 to the negative 1/2 dx dt. Okay, so I can multiply that times 2 real quickly there and get 4. And that'll get rid of the 1/2 on the right-hand side. 25 to the negative 1/2 is 1/5 dx dt. And multiply both sides by 5, and again, very simply, I get dx dt is 20. When you're looking at these problems, like your dy dt, that means the rate of change of y with respect to time. So you're looking at your vertical component, how quickly your vertical component changes with respect to time. Dx dt again would be the horizontal this time. So the rate of change of the horizontal component with respect to time at the point x equals 25, and at the point on the one above where x equals 4. Okay, so we're looking at things with respect to time. A little bit different perspective. This one says find the rate of change of the distance. That's a big thing right there. Between the origin and a moving point on the graph of y equals x squared plus 1 if dx dt is 2 centimeters per second. Well, running through this pretty quickly, if you were just hitting it, you would probably jump right in, take the derivative of that right there. But that's not going to give you the distance. Okay? What I'm looking at is a picture of a parabola. X squared plus 1 means my vertex is at 1. So this nice little parabola coming in like this. And then I have a point that's moving different places around this parabola. And I want to see the rate of change, the rate of change of the distance between the origin and that point. Okay, well, if I want to do the rate of change of the distance, I better write down the distance formula. I'm going to take the derivative of that. Okay, distance formula, hopefully we remember, x2 minus x1 squared plus y2 minus y1 squared. No problem. Okay, well, x2 and y2 are going to be the point that I am moving to, but x1 and y1 are going to be the origin. Okay, because it said the distance between the point and the origin. So that makes my distance become the square root of, and we can drop the little 2's because the numbers that we find are going to be the point. Now I could take the derivative right there, but it would be, whoa, so sorry y'all, I just noticed that I had my 2's down instead of my 2's up. X squared plus y squared, I told you we were going to drop them and I dropped the wrong ones, sorry. Okay, so my deal on this right here though, is that if I do all this, all that it gave me was dx dt. If I take a derivative right now, I'm going to have a derivative of y. I'm going to have a dy dt, and I don't have any values for that. However, what I know is from right up here, y equals x squared plus 1. And I'm going to plug that in right there. So my distance then is going to be the square root of x squared plus, and in place of y, I have x squared plus 1 squared. Now that it's all in terms of x, my dx dt is going to work great. Okay, what I'm going to do is go ahead and simplify that just a little bit, and y'all can do that pretty quickly with me. X squared squared is going to be x to the 4th, and then if you pull that out, you would have a 2x squared, but with this one right here, that's plus a 3, x squared, and then plus the 1 at the end. So there is my derivative right there, or there's my distance, excuse me. Now let's find the derivative. So I have dd dt equals 1/2 times x to the 4th plus 3x squared plus 1 times, to the negative 1/2, excuse me, times, by the chain rule, 4x cubed plus dx dt plus 6x dx dt, and that should take care of that because the derivative 1 is 0. So plugging in my dx dt is 2. I have 1/2 times x to the 4th plus 3x squared plus 1 to the negative 1/2. When I plug a 2 in for dx dt, that will be times 8x cubed plus 12x. Okay, because dx dt is 2 there as well. Okay. If I simplify and reduce this, then my final values for dd dt are going to be, because this is a 1/2 right here, and I'm going to cancel it out with the 2 that I just put in through there, I would get 4x cubed plus 6x all over the square root of x to the 4th plus 3x squared plus 1. Okay? And then I can plug in whatever x value I want, and that will give me the rate of change of the distance with respect to time. Okay? And so that should take care of it. Not a big deal there. All right, now let's look at a related rate problem where we've got 2 trucks, okay, an actual application problem here. 2 trucks are traveling along 2 roads. One road is a north-south road, the other is an east-west road. The roads intersect in downtown Flea-Itch. Yes, Flea-Itch. One truck is northbound and is going 60 miles per hour, and the other is eastbound and is going 40 miles per hour. If at a given time the northbound truck is 10 miles north of Flea-Itch and the eastbound truck is 20 miles east of Flea-Itch, how fast are they moving apart? As quickly as possible, right? Nobody wants to be in a place called Flea-Itch. Okay, so one road is north-south, the other is east-west, going like that. Okay, they intersect right here. This right here is your Flea-Itch town. Okay, the truck that is going northbound is going 60 miles per hour. The truck that is going east is going 40 miles per hour. If at a given time the northbound truck is 10 miles north, so we'll mark it right about here and call that 10. And the eastbound truck is 20 miles east, so we'll mark that right there and call that 20. Okay, then I want to know how fast this distance right here between them is changing. Okay, well, this one's kind of nice. The last one was kind of a pain because when I did distance, I was looking at a parabola, so it was a little tougher. This one, as I look at distance, as these continue to move out and out and out like that, I've always got a nice right triangle. So I don't have to use that kind of strange distance formula where it's a little bit vague. This is exact. I can use Pythagorean theorem. I am in good shape. Okay? My distance here I'm going to call x. My distance here I'm going to call y. And this right here I'm just going to call it capital D. Okay? So that means that my distance squared equals x squared plus y squared. Okay, take your derivative, no problem. 2d dt equals 2x dx dt plus 2y dy dt. Yeah, you can do that, not a problem. It's just Pythagorean theorem and then taking a derivative, which you're good at. Okay. Your 2's, there's a 2 all the way through that we can drop on this. Okay? And so I'm going to divide everything all the way through. Oh, that's terrible. I divided both sides completely by 2. And so we have our d dt equals x dx dt plus y dy dt. Okay, plug it in the numbers that we know. Okay, I'm supposed to find d dt, so that I do not know. Do I know d, the distance? Well, I know that it would change every time as they continue to move out, but at this instant, when my x distance is 20 and my y distance is 10, I can find the exact value of d at that particular second, and that's what I want to do. So if I put in here 10 squared plus 20 squared, that would equal my distance squared. That's going to be that hypotenuse. So that means that my distance value right there would be the square root of 500 when I simplify that out. Okay, so I'm going to put the square root of 500 in. So I'm going to square root of 500, d dt equals my x value, we said was 20, and my dx dt is my rate of change of x with respect to time, which is 40 miles per hour. Plus my y value is 10. My rate of change of y with respect to time is 60 miles per hour. And so I end up right here then with 800 plus 600, so 1400 over square root 500 will be my d dt. So let me grab my calculator. That is 62.610 miles per hour. Okay. And so there we go. I think that looks good. There's our rate of change. How fast are they moving apart? I had another screen in case it took us a lot more space, but it didn't. And so when you come in, we'll start to work on the related rates for Conehead's worksheet and see if we can get that knocked out. Y'all have a nice evening. Bye.